All right, so let's come back to our content. And now that we kind of switch gear a little bit and talk about like basically post PhD and like tracks, like career path. Earlier, while we are taking an extended break for the class. So let's resume and talk about the GPU, right? Because if you look at the GPU in modern system, basically, I can buy a GPU to play these games, right? Uh, and I did actually play all these games. But at the same time, right, not just being able to render cool graphics or animation, the GPU can also be used to run normal application, right? But certain applications would benefit quite significantly from using a GPU, such as machine learning, where many of you guys are using right now. Computer vision, linear algebra, math algorithm, domain-specific application. These are some of the application types that would run really well on a GPU, right? And there's also like server-grade GPU these days where you can run things in the cloud, right? You would use the like A100, for example, is a good example, but GPU in the cloud that you can use right now. I believe VISTEC has one, right? Thai SC also has another set of A100. I think Chulalongkorn also has another way of A100. It seems like everyone is buying that particular GPU. Like the sales team, NVIDIA sales team is really doing its job well in Thailand. Joking aside, if you look at the GPU, there's a few fundamental concepts that we learned from this class that are the primary building block of how GPU run their things. First is SIMD. Second is fine-grained multi-threading, and the third is kind of like they borrow some idea from predicated execution. So let's go with SIMD, right? So we talk about VLIW, very large instruction word. SIMD is essentially single instruction, multiple data, right? So basically, let's say you have an add instruction, right? Now the add instruction typically would be adding two number, right? But SIMD would allow you to add, say, a bunch of number together, right? Parallel add operation. And this is possible on SIMD. Basically, think of VLIW, but now you have one fetch, one decode. The compiler would then spread out all this operation everywhere, right? And execute that code in a SIMD manner, right? Codes that are useful for SIMD are things like, for example, parallel for loop, where you have pragma OMP, right? In this case, this is a bunch of add, right? Add AI plus 1 on every single element of A and write the result back into B, right? This is actually really good for GPU performance because first of all, there's no dependency. So everything in here can be done in parallel, right? Everything in here can be done in parallel. So this is really, really SIMD friendly, right? Why? They are the exact same operation. So this is one of the most important thing about GPU programming. Your program has to do the exact same operation over and over and over and over again, many times. Then the GPU would run really well. So that's the benefit of SIMD and the GPU. The second key concept the GPU use is fine-grained multi-threading. So traditional multi-threading works this way, right? I assign a thread. I use the thread to run on the CPU. Each core would pick one thread to run, right? And let's say you have multiple threads on right now. Say you have Google Chrome right now, right? You also have Microsoft Teams. You have also not Linux, my bad. Mac OS or Windows that have to schedule a bunch of tasks, right, on your computer. You might be also have YouTube opening or audio driver that are running right now, right? The OS would work with the hardware to figure out which thread to be scheduled on the CPU and would pick right? It would pick which thread at any given time that are running. And it keeps rotating between all the threads so that when you run, right, when you run the CPU, it's as if every single program is being run right now. But in fact, you only run threads on each of the CPU at that moment, right? Now, here's the new concept for you guys. You can actually do multi-threading in hardware. So this is what I said earlier here is software multi-threading. Software multi-threading basically allows the OS to context switch. So you switch between tasks using the OS, and that can take a few thousand of cycles, right? It takes some time. Basically, why? You need to save. The time it takes is, first of all, you have to save context, right? Save context. What are these contexts? Program counter, right? Register value. These are some of the things that when you switch to another thread that are running, you need to save the old program counter so that when you switch back, you can resume the execution of your program. Then you save the register value and save all the states required for that thread. Right? So this will take some amount of time. This will take thousands of cycles, right? What if we want to do this in hardware? What if, right? For example, we can do something like hardware multi-threading. We have multiple program counter in my CPU. I have multiple program counter for each thread. I have multiple copy of the register file for each thread. But then when I want to do context switch, I just switch directly to another set of context, right? So the benefit is, even though you have one CPU to run things, so you have one core to run each thread at a time, if one of the thread run into a load instruction, for example, it takes some time to go to DRAM, right? 100 cycle. In the meantime, you switch to another thread and run. This is the idea behind the technique called simultaneous multi-threading, right? This is one of the more really high impact idea where you perform hardware multi-threading and the processor, let's say it's waiting for the memory or the L2 cache miss or L1 cache miss, right? You then switch to another thread to keep the pipeline full. Some example of this is, for example, Intel hyper-threading technology that maintains 2 threads, right? So basically you have thread 1 and thread 2. Again, as I said, only one of them can run at any given time because you only have one core. So this is the CPU core. The CPU core, right? You only have, let's look at one core, one processor. Only one thread is running when it's stalling because of load instruction. For example, it's waiting for the data from DRAM. I switch and run the second thread. And now let's say the second thread run into another DRAM access. I then switch back to the first thread, right? This way, the CPU is always active, running something useful, right? So this is simultaneous multi-threading. Usually you maintain a few contexts so that you can run 2 threads, for example, in parallel. Fine-grained multi-threading put this idea on steroid. Basically, about any pipeline style whatsoever. For example, you have 5-stage pipeline. Every time I move to the next stage, I switch to another instruction. So here's the idea. Let's say I have a 5-stage pipeline. I fetch, decode, execute, memory, and write back, right? Cycle 1, I would run thread 1 here. Cycle 2, thread 1 move to decode, right? Thread 1 move to decode. I then run thread number 2. Cycle number 3, thread 1 move to execute, right? Thread 2 move to decode. Then I put thread 3 into the fetch unit. Cycle number 4, thread 1 move to memory. Thread 2 would move to execute, thread 3 move to decode, and then thread 4 move to fetch. Cycle number 5, I have T5 in fetch, T4 in decode, T3 in execute, T2 in memory, and T1 in write back, right? This way, let's say I have 5-stage pipeline. First question, let's assume the memory is free. Let's assume my memory is free. Do I need to stall the pipeline ever? Do I ever need to stall the pipeline? Will there be any data dependency problem คำถามอีกรอบนะครับภาษาไทยก็คือถ้าผมจะยัด thread 1 thread 2 thread 3 thread 4 thread 5เนี่ยใส่เข้าไปคือทุกไซเคิลผมจะใส่ thread ใหม่เข้าไปแล้วผมมี pipeline 5 stage อ่ะผมจะมี data dependency ได้ก็ต่อเมื่อถ้าสมมุติผมมีคำสั่งของ thread 1 อยู่ตรงไหนใน pipeline ใช่ไหมแล้วผมมีคำสั่งอันต่อไปของ thread เดิมก็คือโปรแกรมเดิมนี่แหละที่เป็นบรรทัดต่อไปแล้วมันมี data dependency อ่ะอันเนี้ยอาจจะเกิดมันจะต้อง store ใช่ไหมแล้วเราก็ทำ data forwarding ทำอะไรก็ว่าไป อันนี้ผมต้องทำ data forwarding ไหมคำตอบก็คือผมไม่ต้องทำผมไม่ต้องทำ data forwarding เลยเพราะว่าคำสั่งที่สองของ thread 1อ่ะมันจะถูกเข้ามาใน fetch ก็ต่อเมื่อคำสั่งแรกของ thread 1เสร็จแล้วคำสั่งแรกเสร็จแล้วทุกอย่างอยู่ใน write back register ได้ค่าที่อัปเดตแล้วใช่ไหมฮะ so what's the benefit here can someone tell me what's the benefit here benefit is you can run 5 threads at a time here, right? And your pipeline is never stalled. You never have to stall your pipeline. You can keep feeding in new thread into your CPU, right? What are the problem here? If you look at, say, thread 1 performance, right? If you look at thread 1 performance, how much is that? What's the cycle per instruction or instruction per cycle? Over here, you're looking at 5 cycles per instruction, right? Or around 0.2 instruction per cycle. This is really, really horrible, right? If you look at a normal CPU, will get you around 3 to 4 IPC in most cases, right? 2 to 4 is the normal number. You can either finish 2 instructions in a cycle or 4. Now, with this particular model, right, you finish only a fifth instruction in a cycle. But now, you also have to have extra logic. You have to have the PC, the program counter for thread 1, another program counter for thread 2, another program counter for thread 3, another set of register for each of these threads. Each of these threads required another set of register, right? So that's why if you look at GPU spec, you will see that the size of the register file is in the hundreds kilobytes of data, which is huge. In many cases, the register file in GPU can sometimes be bigger than the size of the cache, right? The private cache, right? That can be something that's possible and it happened. What's the benefit here? The benefit, again, you never have to stall. So your throughput, your aggregate throughput. So if you look at every single thread combined, the throughput is really high, right? This also means that you need to write a really, really parallel program. Your program has to be highly parallelizable, right? Now, the third thing is the GPU use something similar to predicated execution, where it convert control dependence, like if else in here, into instead of using branch prediction, basically, you use predicated execution, right? You convert control dependence into data dependency, right? You use conditional execution. If this is true, add, subtract, multiply. If this is not true, then do something else, right? So the benefit is you can get rid of any prediction whatsoever. You don't predict, right? And you have a larger code block for a compiler. So there's a recap on predicated execution again, by the way. The downside is you have useless work that you are basically doing if you have a bunch of if else, right? And requires additional hardware support. So the GPU is basically SIMD. Okay, just again, quick recap on SIMD. One instruction, multiple data, right? The idea is the program pointer point to the same instruction and it can perform the same operation on multiple data. The GPU is basically SIMD plus fine-grained multi-threading. FMT is fine-grained multi-threading. Multi-threading, right? SIMD is a single instruction, multiple data, or single instruction, multiple thread, right? So the way things work is this, right? let's say I have a CUDA or OpenCL program. Let me double check. Why do I have this node up? Let me delete it. My bad. So let's say you have a CUDA program. What happened is the compiler NVCC would compile into a unit called thread block, right? Where each collection of thread in a line would be called a warp. There'll be a bunch of thread block in your program, right? Basically, let's say you spawn 10,000 threads. There'll be a bunch of thread blocks that contain all those 10,000 of threads, right? And then your GPU would have the simultaneous multiprocessor. This is analogous to the CPU core, right? And then each thread block would be sent to each of the SM or simultaneous multiprocessor, right? And then at each cycle, a warp, like one of those lines, will be sent to the execution units to process the instruction. So in one cycle, you basically, for example, in this case, you are performing 8 operations per core. So let's say you have 3 cores, right? You send all this thread block to the GPU, and each cycle, you then perform 8 multiplied by 3, so it's 24 operations. So you can imagine this will increase the throughput significantly. One thing I would like to tell you is when you read specification and you see CUDA core, this is just one execution unit, not an actual core. These are some of the NVIDIA PR thing where they say, hey, we have a bunch of CUDA core. It's not an actual core. These are one processing unit. It doesn't have the fetch unit. It doesn't have the decode unit. These are not a core. What can be looking similar to the GPU, the CPU core is something like the simultaneous multiprocessor or the SM, right? So that's one thing I want you to make sure you are aware. And that's coming from a guy whose thesis is on how to design GPU. All right. So let's go back to the 5-stage pipeline that we have in class, right? You have fetch, decode, execute, memory, write back, right? For the CPU, you have things like instruction cache, the decoder, ALU, load store unit, write back phase, branch predictor, out of order execution, right? And the SRAM cache for your data. Everything here are there to improve single thread performance. Well, there are things that are there to improve multi-threading performance as well, but a lot of this component would improve single thread performance. If you design a GPU, basically, you don't need branch predictor. That's predicated execution. You don't need future file. You don't need out of order. There's no out of order in GPU. Everything is in order pipeline. In order pipeline, it doesn't even have data forwarding in some cases, right? Then because you need to support SIMD, you have tons and tons of adder and multiplier. So the execute unit is much bigger. You also need to support a lot of context. So the register file will be a lot bigger. Then you have small SRAM cache to make sure it's fit within the same the chip, right? So many of the things that are added here for the GPU side is there to improve instruction throughput, And when you compute an instruction, you'd run one instruction at a time. Basically means you run one warp at a time. And that one warp would contain one instruction per lane of execution. Each lane would have its own register file, and you perform multiple operations in one cycle. So your throughput is really, really, really high. If I have instruction that takes more than one cycle, the GPU would handle stall this way. So let's say I have a core that has 4 warps for A, B, C, and D. Each box here is one thread, right? So in each cycle, the GPU would basically pick one of this warp and it would run in lockstep. When I said run in lockstep, it basically means that each thread here get run together. So it will keep running, and each cycle, it would pick one of these warp and we keep rotating which warp gets to run on dispatch the instruction into the pipeline, right? And then let's say warp A has a load instruction that takes a while. The GPU core would then basically rotate between B, C, and D, right? So that way, GPU core is actively running something. That's why the throughput is a lot higher. And in the case where you have a bunch of memory instruction, you issue, like right now, for example, you issue 32 different loads, to DRAM, right? This can take a while. So this is the time where GPU stall, and then once some data are back, it resumes the execution and becomes active again, right? So as you can see here, that's definitely trade-off. So you have a really high throughput machine. The instruction per cycle is number of lanes multiplied by number of cores, or the number of CUDA core. That's the maximum instruction per cycle that you can get. But if you look at single thread performance, that's horrendous. That's like really, really, really bad. Each thread would perform really poorly, but you can run so many threads at the same time. So the total instruction throughput is really high. That's why certain applications get run on the GPU and it's really, really fast, while some other instruction get run on the GPU is really, really slow, right? It doesn't have out of order scaling, doesn't have branch predictor. And the performance of your program depends on whether you can run many things in parallel or not. If your code has a lot of critical section, it's not parallelizable. And when you parallelize it, it's not the exact same instruction, then the performance will tank. It will go down so much that you don't ever want to run them on the GPU. That's the trade-off, right? So this is one thing I want you to get away from this lecture. GPU is not perfect. It does have a huge trade-off. Your code can be really fast or really, really slow based on the nature of the algorithm your code is running, right? The use case is, for example, graphic application. The graphic pipeline has a lot of redundant instruction. Draw dots, 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 dots. Draw the line, so to connect the lines to draw the triangle, and then you raster the image to convert the vector into bitmap. Then you smooth out the surface. You then have the texture mapping and draw the surface. Then you determine what object need to be shown in each pixel based on the camera position. These are a lot of linear algebra and linear equations, right? So it's a bunch of add and multiply all together, and you do this on repeat. So these are really, really, really nice to run on the GPU. Then the next problem is you have control flow instruction. So this is where predicated execution comes into play, right? So let's say I have this if-else statement, right? If A is 0, you do something, right? So the status of your code is if A is 0, you do this part. If not, do something else. And let's say for these 8 warps, right? 3 of them are true and 5 of them are false. What GPU would do is it will first run the first half, and the other false threads would be masked off. I don't run anything there. Then I would also run the else part. So as you can see, the entire if else get run unless everything here is true or everything here is false. So that's the big problem in GPU as well, because when you have if else statement, it doesn't do one part, it do both parts, right? So this problem is called branch divergence. For the earlier example, you did not actually utilize all the execution unit at once, right? You run only half of them. This actually lower, right? Lower the GPU performance. So consider this example, right? Let's say you have the core has 64 lanes, right? And every time A of I modulo 3 equals 0, you run this instruction. So this is instruction 1, right? This is instruction 2. This is instruction 3. This is instruction 4. A quick question before we now then take a break again is, what would be the GPU core utilization that I get from here because of my branch divergence? Again, this is based on the value of AI, right? A of I. And let's assume A of I equal 0 for 1/3 of the time, right? And A of I is 0, like, is uniformly random. right? So basically, the chance that I have AI equals 0 is 1/3 everywhere, equally everywhere in AFI. All right. So what will be my GPU core utilization? So now let's do a 5 minutes break. We will be back at 11:30, and we'll come back to this question and we'll talk about so what will be the answer to this? All right.